My name is Michael. I work for Erlang Solutions, and I'm going to talk about type classes, what they are, and how they may be of use to you as an Elixir programmer. And you'll get to see some Haskell as well. So let's get started. When I think about the programming languages that I'm familiar with, I tend to categorize them in two bunches. The first one being those that I feel productive with, that I can get work done with, and the second one being those that inspire me somehow. This is, of course, there are more languages. Of course, there are all of the others, but for the purpose of this presentation, we're going to reduce it over to this lot. Also, just to be clear, of course, it's not necessarily this cut and dry. You could represent this as a spectrum. One should probably acknowledge that some can be both. But the dichotomy of this kind is, this dichotomy is useful for my talk, and we'll run with it. If you have this dichotomy, we can think of related words for how we would describe these. For instance, if you feel that you have a language that you feel productive with and another that inspires you, you might feel that the former is one that you feel comfortable with, and the second one being inspiring because it is challenging in some way. And relatedly further, in your workplace, you might consider that productive language that you're comfortable with as the responsible conservative choice, with the other language being something more experimental, maybe warranted in certain situations, but nonetheless experimental. So we'll go back to these words, though, because they'll have some benefit throughout the talk. Now, we'll use Elixir as the productive one. That's how I perceive it. And Haskell as the inspiring language. Now, for those of you who do not know Haskell, it's a purely functional language that's statically typed strongly. I should reword that somehow. It's about 30 years old now. It is a research language for researching programming language theory. For the longest time, I think they still do actually, they had this motto of avoid success at all costs. The reason for which, if you start being successful, you suddenly need to care about the industry and how people use it and their applications. This has happened to some degree by now, and they're actually a bit more careful how they mess about with their research language. But it is from being a research language that you get this kind of view that some people have, the ivory tower of Haskell, that in the landscape of programming languages out there, the tower rises from the ground, and up there in the clouds, the Haskellites get to pursue their arcane arts, and we, down at the ground, the practical programmers, can only look up in awe at this frightening amount of imposter syndrome manifested in this tower. And it is in this kind of environment that you'll get to hear words such as semigroupoid, contravariant, monad, to mention one. And you hear these arcane spells and like, what is this stuff? You try to invoke these spells, and the only thing you notice that they do is that they clear everyone who wants to get actual work done, just get cleared out from the room. You do something like co-monad, and one person disappears. Traversable, and the whole room clears. I've got a meeting somewhere, not here right now, and it all makes you wonder, what's this for? What's the purpose of this? And to arrive at the bigger question, what are these arcane spells? I think that a first step to understanding them would be to consider them, all of these spooky words, that they're design patterns. That's a word that some people can relate to, but that's still not maybe particularly, that's still abstract. So let's consider this then. We already know some Erlang spells that may be arcane to someone from outside of our community. If we say such things as GenServer, Supervisor, Actor, Process, these are concepts which invoke structures which you can then inject your logic into. And without knowing them, they sound abstract, and without the specific usage of these abstract concepts, which then need to have a specific implementation, they sound hollow, but when you actually use them, we all know how much value these carry. So these are the Erlang spells. If we go to Elixir, we have more spells: enum, stream, task, genstage, and I guess you could also mention Broadway these days. These are all also spells which have meaning within our environment and give something to developers that is abstract, but yet we know it has uses. You just need to know the full scope of what they mean. So let me introduce you to just a few Haskell spells. We'll go with two. We'll see how deep we get into each one of them. The first one being, well, typeclasses. Let's explain the word that is present in the talk title. So a type class is a type system construct that supports ad hoc polymorphism, which is achieved by adding constraints to type variables in parametrically polymorphic types. Got it? Anyone who wishes to explain that to me? Also, by the way, a monad is just a monoid in the category of endofunctors. I'm sure you have heard this one before. So, how about we give this a more understandable definition? A type class is an interface. Just you could go back and think how you feel about enum or GenServer. Like, think about those things which we saw in previous slides. A type class, if in languages that have type classes, is an interface. There are some associated rules, and they're often referred to as laws. So we'll start with a very simple type class, which actually has no laws, which makes it will look like an interface. And for those who are not familiar with, who would want an interface to picture, think of protocols in Elixir. That will be a direct translation. So here's EQ in Haskell. Here's some Haskell code, by the way. Don't be scared. Close the doors, by the way. Don't run away. If you would want your custom type to support equality, that you want to compare, and this new thing that you made, apple, like you want to compare, is this apple compared to this apple? You have to, we have the EQ interface, which we want to fulfill equality for, or rather implement that function for. Haskell also has so it takes any type. The function will take two arguments. That's why there are 1, 2, 3. Of any type and another one of any type, and it will return a Boolean. Haskell also has the ergonomics regarding this specific interface that you only need to define one. Like, you don't only need to define either equal or not equal. It will fill in the rest. So that's just a minor detail. Now, we're going to define an algebraic data type, which is an interesting concept, which actually is present in an Elixir library, which I will mention later. We'll get to it. Where if I would want to define the type traffic light, I can have functions require that I need to get a traffic light, and the actual values that a traffic light can have that you can match against would be red, yellow, or green. This algebraic data type, you could, if you don't feel this like, how would this work? Just imagine that you have a struct that's named traffic light, and it has one field called value. And that value can only be red, yellow, green. So that, if you feel a bit confused, think about that way. Now we get to implement the interface. So we want to create an instance of the EQ type class for traffic light. And this is just standard pattern matching. Is there anyone who is confused by this slide? Show of hands. Anyone? Don't be shy. Actually, who feels very confident about that they understand everything in this slide? Hands up. Okay, at least a few. So there is hope. Next one. So we have implemented EQ for traffic light, and there's a standard library function called nub. If you have duplicates in your list, plucks out the duplicates. And we can do this. Nub takes, as you can see, something that supports the type class of EQ, and it just wants a list of those A's, whatever those A's are. And now we support that for traffic light, so we can throw in traffic lights into a list, and Nub will see that, oh, these are traffic lights. I know, it has EQ, so it can remove all of those superfluous reds. So this is just an interface. Let's move to something that is an interface and has laws, and that would be Funktor. You have all actually used a Funktor, and that is lists. We'll see more about that in a second. So Funktor. Funktor has one function. The interface is just one function, which you need to implement. The laws we'll get to later, but just one function, Fmap. Implement Fmap. It takes, the function Fmap takes a function which takes one argument of type A, returns type B. It also takes the actual Funktor, which needs to contain A's, and it will return a Funktor, which will contain B's. Now, this sounds abstract, but have you ever used map in Elixir, or Erlang for that matter, or any other language? Well, that is exactly what you do. You give map a function, you give it a list of A's, and it will return a list of B's. Of course, A and B can be the same type, but we have to be able to differentiate. And in fact, the Funktor, if you would implement the interface of Funktor for lists, if they, for some reason, if that would not be a thing, that you hadn't implemented it, then you would just implement it this way. Like, we already have map for lists. But now we can treat maps like Funktors. Maps would just be the special case for lists. What is the value of this, you wonder? We already have map for lists. Well, Fmap allows you to reason about something that you say is a Funktor, that you can interact with it like every other Funktor. What could another Funktor be in that case? Well, let's imagine a tree, for instance. The A is just whatever type. We could say integer, string, doesn't matter. So we can, if we define it once again with algebraic data types, the tree can either be defined as an empty tree or a node, which will have a value, and then tree left, right. And this is a recursive definition. So this is a tree, and we wonder, hey, I want to be able to map over a tree, and that may be something that you hear and think like, wait, I know how to map over lists. What does it mean to map over a tree? Well, if you do implement the interface however you want to implement it, however you want to implement the notion of mapping over a tree, defined over here, I provide a function, I provide the Funktor, and I return another Funktor. However you want to implement that, however you want to describe that, then it is a Funktor as well. And you can also then use Fmap. In this case, we decide that if it's an empty tree, we don't do anything. It's empty tree, just return the empty tree. And in the case of if we want to apply it to a tree that has nodes, well, then we apply, where is it? Yes, there is the node. We apply the function onto the value in the node, and then we recursively fmap down on the branches. And now we can say, for instance, if we have a tree of integers and we just want to turn those integers into the string representations of those integers, we just say, okay, map toString over this tree. And we can do that now with Fmap because we support the Funktor interface. Or the trees are now Funktors. The only laws that you need to know, or the laws that exist for Funktor, they exist mostly so that you don't surprise users of a Funktor. This applies to all type classes. The first one is id. So if you're not familiar with the id function, we don't have it in Elixir, but in Haskell and many other languages it is standard. Id is just, I return what I got. Like id of 1 is 1. Id of hello is hello. It doesn't do anything. And the first law is if you fmap id over whatever Funktor, it shouldn't do anything. Actually, you should get the same thing back, which may seem obvious, but that is a law that's required. And the second one is that you should be able to compose functions instead of composing two functions and doing fmap twice should be the same thing. If that sounds a bit incomprehensible, then picture doing enum map on something, and you, let's take that list of numbers, enum map, you do, let's say, toString on all of them, and then you do another enum map with, let's say, add another character add an X at the end of every number string now. You could both do the two enum map, but you could also do enum map once and do both of those functions. That's what that means. It requires you to, those should be equivalent. If you fulfill those laws, then you have a functor. An example of an evil functor, which would then violate these laws and be surprising, would be if you, for instance, map over a list of integers and you get double the amount of elements. That would be surprising, and there you're breaking laws. So what are functors? In some sense, no, not yet. What are functors? Well, they're an interface. There are some laws. And you might think like, wow, we got really abstract now. But let's go back to the GenServer. What is a GenServer on its own? It's nothing really. If you just say, what is GenServer? It doesn't mean much. But if you wrap something in a GenServer, then you understand, like, oh, okay, it's a wrapping concept which has an interface, and it has certain expectations that we have about how we talk to it. Oh, and it's me that actually then injects whatever it is that I want to express into that interface. Then maybe that helps you understand the notion of functor, and functor being the most simple one. Think about, like, how can I interact with lists in an abstract way? So I don't know if I'll be able to talk all about applicative. I'll give you the... No, I think I'm going to have to skip it. But applicative is the next step. Like you have something that already is a functor. If that type also supports the applicative type class, then you can have, for instance, say, a list of things. The functor in this case would be lists, and you can have a list of functions which are then applied to all of another list of things, and you flatten the results. I unfortunately won't be able to go over the details of applicative, but you are encouraged to explore it on your own. And those are the laws. They're actually way crazier. These I would skip anyway. They're way crazier than functors. So understanding type classes. I guess in the end, however, a functor is simply what it is defined to be. The wise student will focus their attention on definitions and examples without learning to lean too heavily on any particular metaphor. If you want to experiment this, if this sounds interesting, that you would want to learn a bit more about these things, then there is a library over in Elixir Land, written by Brooklyn Zelenka, known as Xpeed, and the library is called, Witchcraft. Appropriately, we're casting spells, right? And it includes some other, it's actually a collection of a couple of different libraries, which you can use different ones that you find the most useful if you only want portions of the functionality. But Witchcraft is where you should head to explore this further if you want to implement this in Elixir. So to conclude, what are these spells in essence? And to tie it back into these practical versus inspiring, they're words. Not more than words, really. But words can have tremendous logical underpinnings, wide logical underpinnings that with meaning of great impact. And I think that you ought to look at these words, learn new words, expand the language at your disposal to be able to express more broad concepts, and finally to understand and see patterns in code, yours and others. There's a great book written by George Orwell called 1984, which explores the concept of the value of both retaining and knowing words, but also destroying them, what the effects of that are. If people don't know words, they cannot express themselves, cannot think. So find some words that are useful to you. Find some words that maybe enrich your capability of reading code and understanding it and seeing patterns. Thank you.
Still 2 minutes for me. You could have gone on for 2 minutes more.
Oh, okay. Well, maybe there's time for questions in that case.
questions?
Sure, I can put this up in the meantime. Where are we? So, can we have another? This one, right. Any questions from anyone? Don't be shy. If it helps, I'm a beginner at this as well. Clearly too intimidating a talk.
Hey, I'm supposed to raise a question if nobody else.
We don't need to talk about monads, it's fine.
Can you give an example of where you found these monads or functoes to be empowering?
Well, I would say if you code in a language, so first and foremost, it is extremely helpful to have a language which can enforce these things. In dynamically typed languages, you have and it is alleviated by such a thing as Witchcraft. It helps, it actually starts enforcing things. But in a statically typed language, you can have an expectation such as, I want to be able, the way I want to interact with this data is by mapping over it. So you implement the interface of Functor, of like, I have something that I generally wish to interact with by applying functions to the whole thing. If that's what you're doing, then that is a Functor. But then it helps if your language at compile time tells you something like, oh, you're using this thing not as a Functor, or incorrectly, or you can only use this thing as a Functor. And the same applies for monads, applicatives. Applicative would be, for instance, an enforce in a statically typed system, an enforced way of this is the only way you can do effects. Like if you have this data, it's an applicative, the only way you can do effects is by using an effect, like IO write or something, an effect impure function applied across this data. That's the only way we can do effects. And then the type system helps you. To give you a more general answer of when are these applicable, very difficult to say. Mostly because they are extremely, it's like answering the question of when would I use a GenServer? There's all kinds of different situations. It is such an abstract and high-level concept that it is much more important to look at the concepts used, like look at your code and think, do I see patterns here? And then it's worthwhile to simply know some of these type classes and see if it matches your use case.
Are there examples where... Thank you. One could ask us a follow-on question, something like, where do you use GenServers? Where are they really, really valuable? And the answer might be, it gives you 5 nines or 9 nines. Sure. Reliability and oh, right. So are there equivalents of that for these functors and?
One should differentiate between the two. Maybe it's that's where the analogy falters. All of these are for handling data, for transforming data. The other one, GenServer. Has in that analogy, the problem of it being for the purpose of partitioning things into processes, right? It has semantics to it. Whereas the others are, is the domain of my activity such that it seems most reasonable to express this with this type class? Like that sounds where this type class fits. Someone simply needs to know a few of them and see where it fits. I hope that gives you some kind of answer.